I want to know if there is a connection between the philosophy of mind and quantum mechanics first.
Yes, this is a very interesting question. And actually, this will bring us to a very important paper that I'm hoping we could talk about from the early 1960s. It was a paper by Eugene Wigner. I believe the paper was called On the Mind-Body Question. I could have the title slightly wrong. But Wigner introduced a thought experiment that I think in some ways connected to his view that there was something connecting consciousness and collapse of wave functions. This thought experiment actually dates back earlier. It's not entirely clear to me who originated this thought experiment, because it first shows up in Hugh Everett's extended thesis. Hugh Everett was a graduate student at Princeton, and was at Princeton at the same time, overlapped with Eugene Wigner. And Hugh Everett originated the many worlds interpretation of quantum mechanics. And he wrote this very long thesis. It's 137 pages. I guess maybe that's not long in an absolute sense. In 1956, 1957, he ultimately didn't publish it. His advisor strongly pushed him to publish a shorter, different thesis. But you can find a copy of this extended thesis, and he opens it up with the same thought experiment. So we know this thought experiment was introduced earlier than Wigner by at least, I guess, 7 years before Wigner's paper, something like that. But that wasn't published. Wigner's paper was published, and so it's most widely attributed to him. Wigner had this thought experiment that I'm going to talk about in a little more detail if you'd like, because I think it gives a good motivation for why one might think that there's a problem with the way that we formulate quantum mechanics at the level of its textbook axioms. So I'll come back to it, but I'll just say that this thought experiment apparently was connected with Wigner's idea that somehow consciousness was related to collapse of wave functions. And I think this creates a potential connection between philosophy of mind and quantum mechanics. But there are other connections. In the many worlds interpretation, the formulation of quantum mechanics that Hugh Everett introduced in the mid-50s, one does run into some basic questions about consciousness and human identity in a universe in which a giant universal wave function is splintering into parallel realities, each of which contain copies of yourself. How do we make sense of this kind of a picture and make it connect with how we think about basic problems in philosophy of mind? I don't claim to have an answer to that question. It's an ongoing mystery, I think. So there are, I think, some interesting connections between philosophy of mind and quantum mechanics. And I think my general attitude has been, anytime you're unable to answer a question about quantum mechanics because you've connected it in some way to the philosophy of mind, and in particular to an unanswered and potentially unanswerable problem about the philosophy of mind, I get very worried.
Okay, let's talk about the wave function, because when we're speaking about the collapse of the wave function, the collapse of something, what is this wave function, and why do you believe that there is none?
That's a great question. So let me say a little bit about some history. I think some history here might be helpful to ground things. But before I do the history, let me first answer your question. I'll give the short answer, and then we'll talk a little bit of history, because otherwise we might get lost in the weeds. There's this popular story about quantum mechanics that a lot of students coming into the field have heard. The first primary object in quantum mechanics is the wave function. It's this mysterious, undulating object. It's a little bit unusual. It's kind of like the electric fields, sort of, except that its values are complex value. They're complex numbers. They're like ordinary real numbers plus a number times the square root of -1. And somehow they're connected with probabilities in some way. And somehow the point of quantum mechanics is wave functions. They're the central player in the story. And how you think about quantum mechanics begins with how you think about wave functions, right? They're the protagonist of this story. There are, I think, some good reasons to be a bit skeptical of that picture. And I don't think that there really is much, there would be much controversy about saying, I think, when you learn about quantum mechanics and you begin to see that there's this much bigger picture, you begin to see that the wave function in this sort of story is a little bit of an oversimplification. I think if you pressed someone who works in physics pretty far, they would admit actually this picture is it's a little bit too quick, and there's a deeper picture beneath it. And so I think there's one view in what I'm saying here, your question, which is just to take those concerns and take them to their logical conclusions, right? Ask ourselves, okay, what does this theory really consist of? Is it really about wave functions at all? And for that matter, are wave functions things that describe objects that are really out there in the world? And this is where one lives in kind of a liminal space between physics and philosophy when you ask questions like that. On one hand, it's about physics. It's about, what's the right way to think about, what's the right way to formulate, what may be our best, most successful scientific theory, certainly when it comes to numerical accuracy and precision. And on the other hand, what's really out there? What's out there in the world? What exists, right? This is this word ontology that metaphysicians use. Ontology is the study of what really exists. And to ask, does the wave function describe something that physically exists? That's a question. So to explain a little bit about how we've arrived here, I could say a little bit about the history, but let me just pause and ask, do you have follow-up questions about this? I want to be careful to make sure we all have time to.
Sure. So when you say that there's the standard picture of the wave function, you said, okay, what people are taught is that there's the wave function, and it's connected to complex numbers, and that it's also connected to probability somehow. Is that the picture that you're referring to, or are you referring to the picture that the wave function represents something in physical space and is of something?
Yeah.
So when I say that, what I mean is when people say the wave function, when physicists speak about the wave function, it's the wave function of something, the wave function of an electron, the wave function of a so-and-so.
Right.
So what is precisely this picture that you're about to shatter?
Yeah, so this is an excellent question. I think the issue here is that it's a little of both, right? The wave function plays a functional role in quantum mechanics. That is, it does certain things for you in the theory. We study its change with time. There's this famous equation called the Schrödinger equation, which roughly says that when a system is left to itself, it's not being disturbed, it's not exchanging information with any other systems, then it has a wave function that changes with time in a smooth way. And this smooth process is described by a differential equation, which is roughly speaking an equation that just tells you what the wave function is at each infinitesimally next moment, given what it was at the previous moment. And this equation is known as the Schrödinger equation. So we plug in an initial wave function, we use the Schrödinger equation to figure out what the wave function how it will behave as time progresses. And then there are rules for taking the wave function and calculating predictions. So that's uncontroversial, and I certainly agree with that picture, that we should be using wave functions for that purpose. But I think it's easy to let that picture lead one to think that wave functions are describing physical objects out in the world. And, when I think students arrive in a quantum mechanics class for the first time, without having studied the theory, they may think that, okay, every particle's got some wave function. The wave functions are kind of like waves empty space is kind of like the ocean, and all the particles are kind of like small little waves moving around in the ocean. And that's actually not the picture that we get even from the textbook theory of quantum mechanics. In the textbook theory, a wave function is the assignment of a complex number to every possible configuration of your system. If you're talking about a single particle, nothing else, then every possible configuration is every possible location the particle can be in. Each location is labeled by 3 numbers. It's x, y, and z coordinates if you want. And so the wave function takes in those 3 coordinates and assigns it a complex number. And then we're supposed to do a mathematical operation at that complex number, and out comes a probability. More precisely, a probability density, but a probability per unit volume that a measurement will find the particle at that spot. So the wave function can be thought of as the assignment of a special complex number to every point in 3-dimensional physical space, where you do this operation. It's called mod squaring. You do this operation, and then it tells you the probability, roughly speaking, with which a measurement will find the particle at that location. So it's very easy to think that a wave function is like a field, like the electric field in 3-dimensional space. But if you have two particles instead of one, then the possibility space is much more complicated. We call this possibility space configuration space, because each possible configuration of a two-particle system requires six numbers, not three. You need to know x, y, and z for the first particle, and you need to know x, y, and z for the second particle. So the wave function assigns a complex number to a point in a six-dimensional space. 6 dimensions because you need 6 numbers to specify its points. And that means a two-particle wave function is a function, we say, whose domain is a 6-dimensional space. 6-dimensional space is not physical 3-dimensional space. If you've got 3 particles, it's a 9-dimensional space. If you've got 10 particles, it's a 30-dimensional space. And actually, our universe does not have a well-defined number of particles at all. Our leading physical model for the universe, at least for the non-gravitational parts of the universe, is the Standard Model, which is based on a set of models known as quantum field theories. And in quantum field theories, particles are emergent excitations of these sort of delocalized entities called quantum fields. And the number of particles can change from moment to moment. It's not always well defined. So it's not even clear how to even think about wave functions that live in anything like physical space in the universe as we know it. So I don't mean to say that we're teaching our students wrong. We're not. I mean, students will learn this as they go on in their physics trajectories. But I think a lot of people on the outside, or new students who haven't yet started their own journey in physics, have a certain idea about what wave functions are like that's actually quite different from the way we use them in practice. I don't know if that clarifies, what you were asking about.
Okay, so you have a lecture about how Hilbert spaces are also not real. I'd like you to talk about that. Now, it's my understanding that you more precisely said Hilbert spaces are redundant in the same way that gauge symmetries are redundant, or the gauge transformations are redundant.
So at this point, if it's all right, let me do a little bit of history, if it's okay. So where does quantum theory begin? Lightning, grand tour of quantum theory. There are these actual physical objects called black bodies. They are chambers that are heated, and a little hole is poked in them. I mean, you don't really poke a hole in them. It's more complicated. But this is I'm very much a theorist, and my picture of experimental physics it should be better. And I apologize in advance to anyone who's an experimentalist listening to me. But these were actual systems. People actually built these things. They were these chambers. They would heat them up, and then they would have a little hole in the chamber through which they could see radiation coming out of them, and they could put that radiation through experimental devices that could show them how intense the radiation was as a function of wavelength. Right? We all know that different wavelengths of light correspond to different colors in the visible range, and if you go outside the visible range, you have very long wavelengths that are infrared or microwave radiation or radio waves, and at the very short wavelengths, you've got X-rays and so forth, gamma rays going all the way out, ultraviolet X-rays, gamma rays going all the way out to very short wavelengths. And you could just ask yourself, if I plot how strong the radiation is as a function of wavelength, what kind of pattern would I expect to see? And the pattern that was revealed in experiments was difficult to explain on first principles theoretical grounds. A very important physicist, Max Planck, in 1900, found a way to generate a theoretical prediction of what this black body radiation curve should look like, and it agreed with experiment. But in order to get there, he had to kind of hack his formulas. He had to introduce a fudge factor. He had to assume that radiation in this chamber could only occur in quantized amounts. That is, there were different wavelengths you could produce, but each wavelength could only be excited in discrete steps. This led to the quantum hypothesis. This was his quantum hypothesis. And there was a sort of parameter that told you how big you wanted to make these steps. Today we would call it a regulator. And this parameter, we now call it h, little h. We call it Planck's constant. Planck introduced it. And then I think at one point his idea was he wanted to introduce an intermediate step in the calculation. And once he'd calculated everything, send this clearly, in his mind, unphysical parameter to zero. But whenever he tried to send it to zero, he would get the wrong results.
As you know, on Theories of Everything, we delve into some of the most reality spiraling concepts from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.